So, welcome back to this NPTEL course on additive manufacturing. So, in today's lecture I am going to continue my discussion on SLM printing of lattice structures, but I will show you that how lattice structures can be printed using stainless steel 316 alloy. So, stainless steel 316 alloy, it has a this D50 so this is the percentage particle size, and you can see particle size varies between 10 to 100 micron. It is a pure gamma austenitic phase, and we are using the laser powder based fusion processes, and you can see that you might have seen number of times that how SLM printing takes place in industry. So, when I was showing you some of the experimental results in our discussion on process science, I have shown you how linear energy density is important, and this you can see that energy density and porosity. If these two things are varied, then you can say there is a lack of fusion related porosity and keyholing related porosity, and this particular curve actually goes down, remains flat, and then increases. So, here what you see in the process map, you have a laser power and you have a scan speed. So, this is the specific region which is the region of the conductions, and you can see that this is the acceptable range without any defect. Outside the region, you will have either balling, the blue one, or lack of fusion. So, this is the balling region, this is the lack of fusion region, and this is the keyholing region. So, these particular regions, there are specific defects which are intrinsic to SLM processes. So, in case of stainless steel 316 alloy, this D10 is 21, D50 is 32, and D90 is 48.5 micron. From the ACM images of the morphology, it should be very clear that it has perfect spherical morphology, which is what is desired or which is required for SLM based printing. So, while constructing the printability map, we have also used the machine learning, but those I am going to cover it in the subsequent lectures. So, what I have mentioned in the discussion of an earlier lecture, that one can vary the scan speed and laser power, and by varying the scan speed and laser power, you can essentially investigate that what kind of defects that it can generate, and those defects can be plotted as a function of the process parameters, and you can see that how keyholing also diameter to width ratio can be changed in this specific region, specific defect region. What we would like to have always in particular engineering applications, we would like to have conduction region. Okay. This is the conduction region, and this is the most acceptable region, most acceptable combination of process parameters which are required. Roughness of the additively manufactured sample, this roughness, you can see this roughness can be around 6 to 8 micron, and volumetric energy density, it can go up to 100 joules per millimeter. And this roughness, as the layer thickness grows, if you see the trend, as the layer thickness goes up to 90 microns, the roughness will also go up to 3 micron. Okay. So, the surface roughness is somehow related, is certainly related to the layer thickness that you use in the additive manufacturing technique. Now, universal testing machine or tensile testing is very commonly used in almost all university research labs, and what particularly important here, this digital image contrast setup, which is being attached to this particular UTM, and also UTM is equivalent to strain gauge. When you have this strain gauge and also DIC setup, you are essentially very sure that you are reliably measuring the strain. Okay. And this strain property, therefore, the elastic modulus values what you report is also reliably determined. So, the use of strain gauge and use of DIC setup essentially are useful not only for reliable measurement, but also to see how the material deforms, how the damage accumulates and progresses, leading to the failure of the materials. So, what you see here, you are essentially seeing that different process parameter combinations like laser power and scan speed and also hatch spacing. Hatch spacing can go from 100 to 140 micrometer and layer thickness can go from 30 to 90 micrometer. So, independent of this combination of the process parameters, what you see here very clearly that the relative density you are getting is very close to full density like 99.8% and above. And when you are using the different type of samples under the different type of samples in UTM machine, what you see that their elastic modulus properties is almost same. If you see the elastic modulus, this is very clear, and then the strain to failure is different. Maximum strain to failure is 80% that is recorded, but for other materials strain to failure is decreased to 60%. And you can see also the yield strength, it can vary from 400 to some around 550 megapascal, which is very common for the metallurgically processed stainless steel 316L materials. Now, what you see also that when you use the DIC digital image contrast, you can always see that at the onset of necking and then how the plastic flow also spreads during the continuous deformation processes. So, materials is experiencing tension this, and you can see the occurrence of the necking, right. And in this particular region you can see that if you step it up at fracture is epsilon 53%, you can see this particular area reduction in cross section area is much more compared to the increase in the length. And this is the case for the uniform deformation. Uniform deformation essentially means the increase in the length is commensurate with the decrease in the cross sectional area. So, therefore, the material deforms very nicely, there is no anisotropic deformation behavior. But in the necking conditions this triaxiality stress condition arises, and in the necking region you have more localized strain, and then also in the necking region the reduction in the cross section area is much more than increase in the length. So, you can see in this video that as the material deforms under tension, then you can just look at this particular region here, that how the necking, I can run this video again. This is the video taken at that materials engineering attendance of science using the DIC setup available at Professor Praveen Kumar's facility. You can see how epsilon YY here, right, that changes. So, it is 2.35 here, and this is the region the necking actually sets in. This is the total area is the gauge length. Gauge length is the area in the undeformed sample, it has uniform cross section. So, having uniform cross section is important because the material is will then experience uniform deformation under the tensile loading, and this kind of curvature, this kind of tensile sample is also known as a dog bone geometry. This kind of curvature and this kind of shape of the sample is also known as dog bone shaped samples, and this is according to the ASTM standard. These particular samples are being prepared, what is the gauge length and what is the initial cross section area, right. So, what I am trying to show you here, it is possible as the material deforms, you can essentially capture the tensile strain, and you can see that one of the strain tensor is epsilon yy, and that essentially you can measure dynamically during the tensile experiment, right. So, one of the things that is very important in 3D printing, and that in the community it is quite known, that because of the nature of the 3D printing processes, one can expect that the 3D printed materials or 3D printed components will have anisotropic properties. Anisotropic properties means that you are essentially building layer by layer materials, right. So, if you consider that in the build direction and transverse to the build directions, the material properties will be very different. Okay. So, if you take the tensile coupon samples, so what I am trying to say, what I am trying to show you is that, for example, materials is getting printed in a layer by layer manner, right. Now, you are trying to see that whether this material will have anisotropic properties. So, you are taking a coupon samples, what we call dog bone type of geometry, in this direction, in the build directions. You also essentially measure the tensile properties in the transverse to the build directions. If there is differences in properties, in almost many 3D printed components, people have reported that depending on whether you measure the properties in the build direction BD or transverse direction TD, the properties will be different, and that is very inherent to the 3D printing processes, and this is what I was telling about the anisotropic properties. So, there is two way you can see that in the horizontal directions, that when you essentially strain them. So, what happens, this is the stress strain plot, and what you can see, this is the combination of V is equal to 500 millimeter per second, P is 180 watt, hatch spacing is 140 micron. AP stands for as processed, and heat treatment 1, there is one type of heat treatment 2, there is a different combination of heat treatment conditions. So, what you see, and then we have taken multiple samples, like for as processed, let us say 3 samples, for HT1 3 samples, HT2 3 samples. We are also trying to see reproducibility in the properties while understanding the anisotropic properties by measuring the tensile properties along the build direction, transverse to the build direction. So, more or less what is the common here in every plot is that the material behave in an elastic plastic manner. Their strain to failure is roughly restricted up to 60%. Okay. In some cases, in case of the in case of the high LT values, it goes up to 90 micron, then the strain to failure decrease to 40%. Otherwise, this strain to failure is mostly 50 to 60%. That is number one. Number two is that ultimate tensile strength in almost all the cases is around 700 megapascal, except in the last plot. However, depending on the as processed to HT1 to HT2, we are able to see HT1 perhaps is giving maximum better combination of the strength and ductility properties. So, essentially what we are trying to see is that strength ductility combination. You would agree with me, irrespective of these process conditions, elastic modulus is constant, and typically this elastic modulus is around 210 gigapascal. There is no difference in the slope. In the case of the vertical case, we essentially see little bit lower strength properties like around 600 megapascal. In some cases it goes above 600 megapascal. Here again, compared to the as processed, perhaps HT1 heat treatment, after heat treatment, the material has better ductility. So, it is not only strength, because strength is essentially quite good, and that is the strength properties one would get also metallurgically processed or conventionally manufactured SS316. What we are more interested to see, because of the inherent microporosity in the 3D printed structures, which I have emphasized in some of the previous lectures, whether we are compromising the ductility property of the materials. So, therefore, I put a star so that you do not forget, in the 3D printed structures it is important to maintain the strength ductility combination. While maintaining high strength is important, but at the same time having good ductility is also equally important. And you can see that different orientation like vertical, horizontal orientations for different process parameters, how you get different combination of ductility, like in all the cases when it is vertically oriented, it has a better ductility. And then strength, yield strength and ductility. Yield strength is also, ultimate tensile strength is lowered, yield strength is lowered. So, essentially horizontal, it has little lower ductility, but better strength properties. Vertical orientation has lower strength properties, better ductility. So, it clearly shows that there is sign of anisotropy in this kind of anisotropic properties in these 3D printed structures. Now, mechanical properties wise, AP is the as processed, AN is the annealed. So, it was annealed in 1095 degrees Celsius 1 hour. These are laser powder based fusion processes. Now, when you compare with the metallurgically processed stainless steel 316L materials, this is the wrought materials, and this is as cast, and this is annealed sample. And what you see here in the as cast, you have 365, this is the yield strength, close to 600 is UTS, and elongation is 70%. So, if you compare with the UTS is close to 600 megapascal and elongation to failure is 70%, 70% is epsilon f, elongation to failure, you will see that even in the present work you are getting almost close to that combinations. But only thing you have to notice that if the strength is 661, elongation to failure is 53%. If the strength is little lower, 544, elongation to failure is 83. If the strength is modest, close to 600, elongation is 69%, right. So, it is possible to optimize the it is possible to optimize the heat treatment conditions in the 3D printed stainless steel 316L to obtain what one can get in the as cast and annealed structures of the same material, right. So, this is the combination that I was trying to show you. Now, what you see in this particular slide is that how complex struts. So, earlier I have mentioned that triply periodic minimal surface TPMS structure, that is the combination of the lattice structures. Now, what you see here in this particular slide, that how one can design different strut thickness in a face centered cubic FCC structure where cell size is around 1 millimeter. So, earlier unit cell dimensions were varied from 2.5, 2.7 and 3 millimeter. Here the strut thickness is varied 160 micron, 240 micron and 340 micron. Now, we have designed these struts. So, more the thickness, lesser is the porosity, interstrut porosity, that should be very clear, right. And if you look at the cell size, it is a face centered cubic structure, but from these particular design descriptions it should be very clear that this kind of complex strut interconnections, it is very difficult to do it in the conventional manufacturing, which is why additive manufacturing has attracted wider attention. Now, what we have done, we have designed the structure, then we have established the 3D printability of the structure or 3D printing manufacturability of the structures. We have not only made these coupon samples, you can see this is the coupon samples, like this is the sample volume 25 by 10 by 4 millimeter cube. So, it is 25 is the long directions, width is the 10 millimeter, height is your 4 millimeter. Now, the same tensile samples you can process and you can measure the tensile properties. Ultimately, when we are satisfied with these either 160 or 240 or 340 micron strut size, we have also fabricated femoral stem of the similar 160 micron strut or 340 micron strut. We have designed the femoral stem and we have essentially made attempts to use the SLM technique to manufacture this kind of femoral stems. Let us see what is the results we have got. So, we have essentially varied the different combination of 3D printing parameters like laser power, scan speed and energy density. So, what is the strut thickness and what is the width, these two parameters were varied, and after varying so many different parameters we are able to get this is the kind of femoral stem components, right. We are also trying to find out that what is the density of the different struts in this particular case, and we have found out that 160 micron, 240 and 280 micron, there is a local thickness of the struts that we have measured, and we have also measured actual strut thickness and how they essentially correlate to each other. You can see the vertical side, these are mostly close to the 45-degree line. In the one is that below, one is above, there that we can see certain variation between the local thickness and actual strut thickness. So, we have done microcomputed tomography analysis. This is a typical analysis that we always do to characterize the 3D structures, 3D lattice structures, and you can see micro-CT images of the different strut size 240 micron to 340 micron. You can see the 3D view of the lattice structures, how they are generated in the as printed structures. So, we have also quantitatively analyzed what is the distribution of the pore size, and what is the lattice design strut structures. You can see while this is the 240 micron, this should be the mean, but how this strut thickness is also distributed across the 3-dimensional space. At the same time, you can see that what is the porosity. Porosity is roughly around 300 microns. It is relatively large size porosity. For typically for osseointegration purpose, the porosity is 100 to 200 micron. So, overall in last 2 lectures, I have emphasized that how 3D printing and one of its or in particular the selected laser melting or directed energy deposition can be scientifically studied to establish the process map of any material, and I have taken 2 model materials. One is a stainless steel 316L and one is Ti6L4V, and both these two model materials I have shown you that not only the construction of the process map, but also showed you the different defects, and all subsequently I have also shown you that how the complex lattice structures, whether it is triply periodic minimal surface structures or this is the complex strut structures, can be printed in with good quality, and what is the quantitative analysis of the strut thickness distribution or pore size distribution, and more importantly how the different TPMA structures of different unit cell dimensions can be constructed and tested to mimic the properties of the cortical bone structures. And there we have shown this larger the unit cell diameters, more is the reduction in the elastic modulus as well as strength properties, and it is possible to mimic the cortical bone properties with higher unit cell dimensions like 4 millimeter or so. So, I hope you are happy to see the different examples in last 2 lectures, and so that you will also firmly believe that 3D printing, additive manufacturing indeed has great potential and has demonstrated its potential to manufacture the complex designed structures in a reasonable and reproducible manner, not only in one materials, but also multiple materials which are of larger engineering relevance. And these 2 materials that I have shown you is Ti6L4V and stainless steel 316L materials. So, I will come back to you with more lecture with other scientific contents that are part of this NPTEL course syllabus. Thank you.